Hey, California Lies Math and History, and we are going to take a look at the work energy theorem. So, in the past physics video, we've been learning a lot about roller coasters with kinetic, potential energy, and we've been solving this when there's a frictionless roller coaster, meaning that if you're on a roller coaster that's frictionless, we tried to calculate, and we did calculate the velocity at different points. We calculated at the top, the bottom, up here, and at the finish line, which probably isn't really ideally a roller coaster for it to work. But what we're going to do is talk about the net work. So in the past physics videos, we've been taking a look at net force and force being applied, but also with centrifugal force, we also talked about the net force of that. Centrifugal force is some kind of net force. And we've been also taking a look at speed, energy, and work formulas. But sometimes people are forgetting that there is something else in play. Normally we say frictionless. However, what we mean by friction is also a force. So basically what happens is no matter what you try to do, if you walk, you push a heavy cart, or if you even pull your backpack and try to run toward your next class, which is 2 minutes apart, friction is actually a force. And also, it also requires some work too. If I'm rubbing on the ground, it takes work for me to rub on the ground, but also friction is acting on it too. This box of gears as well. When I'm pushing on here, I'm performing work. But also, friction does the work to do the exact opposite. So many people forget that friction is an actual force that goes against it. But also what we say is, the more work something does, the more friction work does too. But the thing is, in order to move forward, friction cannot exceed more work than the force being applied that you're applying. And that's when we can say the work net is going to equal the mechanical energy that we have. Also, we are going to look at the work energy theorem, meaning the total amount of work is going to equal the final mechanical energy that you have at the end, subtract that by the initial mechanical energy at the start. Similar to, you know how we have at the roller coaster, the initial mechanical energy right here? That is going to say that when you get to the end of the roller coaster, which it shouldn't be way up there, your mechanical energy at final is going to be a lot different. It could be higher or lower. Well, lower if you're using gravity, but higher if, aka, you're using those rocket boosters on the roller coaster. We can also say mechanical energy initial plus the work will help you find your final mechanical energy. But what we're going to do is, to understand when we say friction is a force and it's also working against you, technically what we're going to do is solve this problem out. So, a 1,200 kilogram car drives at 25 meters per second. What is the required friction in newtons to slow down the car to a complete stop? So, we have a 1,200 kilogram car right over here. It's going at a velocity of 25 meters per second. What is the required friction to stop the car? So we know that what we're trying to do is try to stop the car. And since assuming this car is on a horizontal plane, meaning there's no hills, there's no some of these, the car is going to go from rolling to a complete stop. So what we're going to use is the kinetic energy. There's no potential energy because we're not trying to overcome something. It's going to equal 1/2 the mass times velocity squared. And sure enough, we have the mass, which is 1,200 kilograms, and 25 meters per second is our velocity. So about kinetic energy, we have to try and solve for the kinetic energy to solve it out. But there's going to be a catch at the end of this video. So let's try plugging in these two things into the formula. So KE is going to equal 1/2 of 1,200 kilograms. Then we have to multiply that by 25 squared. So half of 1,200 is 600. But also, 25 squared is going to be equal to 625 when we multiply. When we multiply it out, we get 375,000 joules. But there is one little issue about the 375,000 joules. Remember what we said about what happens when you try to do any kind of work? Using the diagram right here, if you're trying to apply work but also apply a force, we realize that work is going to help you complete that task, but that so-called friction is going to be working against you. The force of friction is going to be working against you. So it's not going to be 375,000 joules. It's going to be negative because we know that friction is going to have an opposite force, trying to make it harder for you to slow down the car. But if you want to slow down the car to a complete stop, that's something that you want to do. Because if there was like a tree in front of you or if there was like a crosswalk, you have to slow down. So that's how much work it takes for the car to make a complete stop. So yeah, that's how we can apply and understand how friction is a force that works against you, and also learn about the work energy theorem, which can help us later. So yeah, I hope this video has helped you understand the work energy theorem. Thank you for watching Top in Your Life's Math Industry. Like and subscribe.